Good morning, everyone. It is my pleasure to introduce the speaker today. He is not stranger to this building. Hakim C. Mohammed was intern in Microsoft Research 7 years ago. Today, he is associated professor in University of Lille and is going to give a talk on his work in the area of brain-computer interfaces. Without further ado, Hakim, you have the floor. Please continue and to introduce yourself. Thank you.
Perfect. Thank you very much, Ivan, for the introduction. I hope everyone hears me well. Yes, the echo makes sense. So yeah, as Ivan mentioned, it's quite a strange feeling to be here after 7 years. It feels all at the same time as a very long time ago and as yesterday. So I'm really happy to be here again, to have the chance to present a little bit of what we've been doing since then at the University of Lille. So just quick introduction about a few words about myself. I have a PhD in computer science from INRIA in Rennes that I obtained in 2019, working on the supervision of Anatole Lécuyer on brain-computer interfaces and augmented reality. And during my PhD, I had the occasion to intern here with Ivan, Andy, and Christian Holz, who's now at ETH Zurich, where we worked on basically SSVEP devices and SSVEP interfaces and how to make them more user-friendly. I will talk a little bit about that later. After defending my PhD, I was recruited by the University of Lille in September 2020, while I was actually supposed to come here for a second internship, but 2020 was a kind of a special year. But yeah, I am finally happy that I was able to join the University of Lille as an associate professor. And since the 1st of January of 2026, I also have been appointed as the deputy head of the Research Federation, SCV, which is a French Research Federation of the CNRS. I will talk a bit about it in a few seconds. Before starting the presentation itself, please feel free to interrupt me instead of waiting the end of the talk to ask questions. Just unmute your mics and I will be happy to answer questions live. So just to tell you a little bit about what is the Research Federation of Visual Sciences and Culture, FRSCV. So it's actually quite a unique structure that brings together 3 labs that are specialized in history, art, neuroscience, and computer science in order to conduct multidisciplinary research with a strong objective of being able to transfer the results of our lab to the creative industries. So we have a strong component of being able to be industry driven and to really transfer our results to the field. We have, as assets, multidisciplinary expertise, people from both neuroscience, computer science, with some AI, and museum, archaeology, and art, as well as a cutting-edge technology platform. For example, we have quite a unique cave system, which is called the TOR, for the open reality experience. It's like a cave or cave virtual environment, but completely round screens. So with no edges to avoid having the artifacts from there. And that is put at the disposal of the researchers and the companies that would like to do experiences in the cave environment. We also have several tools for physiological measurement, like electrodermal activity, of course EEG that I will talk about more, motion capture, and also photogrammetry. So we really have all the expertise and the tools in order to be able to be at the forefront of the research with the companies and the industry with this particular positioning. So about the talk today, the progressive approach that I will adopt is to start by talking a little bit about brain-computer interfaces as a whole, trying not to make like too much of an in-depth description. Then I will talk about some of the results or some of the works we've been conducting on merging or combining BCIs with immersive systems. What I call immersive systems here is AR and VR, augmented and virtual reality. And then I will end up with Neuro-Adaptive systems, also called passive BCIs, which is for me one of the ways or the most promising ways of getting BCIs outside of the lab. But we'll talk about it in a few moments. So let's start with a small experiment that I like to do during my talks. just to make sure that everyone is on page on, I know most of the people here in the room are familiar with the concept of brain-computer interface, but it's good to have some common ground to be sure that we are on page on the definition itself. So let me ask you to imagine a brain. Just figure it out. Imagine a brain. Quite easy, right? Everyone has one. Most use one. Yeah. But almost everyone knows what it is. So it's quite easy to figure out. So now try to imagine a computer. Again, pretty easy. Some of you may have imagined maybe a laptop, some other desktop, but we know the concept of a computer and we understand what it is. So now you see me coming. Imagine an interface. It's harder to picture, right? It's not that easy. And that made me think that in the term brain-computer interface, while a lot of people focus on the brain part of it, saying that it's a technology for reading the brain, actually the word that helps most define the concept of brain-computer interface is the word interface itself. So as any good researcher would do, I Googled the term, and I went to the Cambridge Dictionary and find out that an interface is the situation, method, or place where two things come together and have an effect on each other. So this gives us the idea that a brain-computer interface is the system that enables both the brain and the computer to interact on each other. And that's not actually this obvious, because the definition of a BCI is still not standardized. There is a whole effort from the BCI Society that has been conducted with a huge poll on 147 researchers in the BCI field, where they presented several questions, a whole survey and proposition of different definitions, where they actually mentioned the unidirectional or bidirectional nature of BCI, whether both should be included in the definition, the source of the signal, whether the CNS, central nervous system in the brain itself, was supposed to be the only source for BCI, or whether we could extend it to other physiological sources, or whether the intention of interaction of the user should be included. And that was specifically targeted to passive BCIs. And we ended up with this definition that a brain-computer interface is a system that measures brain activity and converts it in nearly real time into functionally useful outputs to replace, restore, enhance, supplement, and or improve the natural outputs of the brain. So the purpose of a BCI, as it has been defined by the BCI Society, is to replace natural pathways, to enhance, restore, supplement, and improve. And we will talk a little bit about it to illustrate how the shift from a BCI moved from assistive technologies for basically people with disabilities for clinical use towards non-clinical BCI usage. As for how a BCI works, there is a closed-loop processing pipeline that all starts with brain activity production. So I insist here on the fact that to be able to operate a BCI, it is important to know exactly what type of brain activity we're measuring and not using it as a black box. Then from there, the brain activity is measured, usually using EEG or other types of brain imaging. And then comes in the whole signal processing, machine learning, and AI part in order to recognize the patterns that are being generated before transforming that into a decision. And then the bidirectional nature makes it that from the feedback that the user gets from the activity, there is a possibility to remodulate the brain activity in order to operate the BCI itself. So, just to illustrate how the BCI have moved from what I call the founding fathers of the BCI, the people who really introduced the first BCI paradigms, which is the type of brain activity that is exploited for interaction, and to today's BCIs that should be closer to be outside of the lab. So the P300 speller itself was introduced in 1988, where the principle was that as a reaction of the brain on a significantly rare or pertinent stimulus, the brain responds with like an activity at roughly 300 milliseconds after that. And that was used actually to be able to make spelling by just focusing on letters that would flicker randomly. The motor imagery was introduced a couple of times later, and it is based on the fact that when imagining moving a hand right or left without doing so, we were able to detect that from the EEG and send commands. That's pretty useful for either rehabilitation, for neurofeedback, or for controlling wheelchairs that I will talk about it. SSVEP itself, that I will talk about more in details later, was introduced in 1995, and interestingly, the first demo of SSVEP was not meant for rehabilitation or for spelling, as it's most of the case now with SSVEP, but it was for operating a flight simulator. So the founding work from Macmillan and colleagues was to be able to control a flight simulator by focusing on targets flickering at different spaces in order to operate it hands-free. And I see how interesting that in 1995 already, people were already thinking about how a BCI could be used outside of an assistive technology for people with disabilities. And that remains still today one of the biggest challenges for the BCI community. And just to continue with the founding fathers and to pay tribute, slow cortical potentials were introduced in 1999. So, as I said, BCIs have traditionally focused on rehabilitation and assistance of disabled users. That was their main purpose, and it still remains the case today. For people who have no other choice, who are not able to operate their muscles, being able to operate through the brain activity itself offers a very promising approach and maybe sometimes a unique solution for them to interact with the outside world. Not to dig too much on a lecture here about the history of BCIs, I just cite here a paper that you can have access to that was written by my good friend and colleague Fabien Lotte, and which really traces the whole history of BCIs from the very first results to today's system. But to illustrate the concept of how a BCI can be used for rehabilitation, I have selected a few examples. For instance, this is a work conducted by colleagues from the Jose Milan labs at EPFL by the time, now he's at University of Texas, Austin, where using motor imagery, a user could think about moving his or her feet in order to advance the wheelchair, thinking right hand or left hand to operate the wheelchair. So this is a very illustrative example of how a BCI could be used to operate an external device, which is called an active BCI because the user is spontaneously controlling the system. And this is an example from colleagues from the Athena group in Nice, in INRIA, of how we can use the P300 in order to spell and send messages. So in here, the user is trying to spell hello by focusing on the given letters. And every time there is a P300, we detect which letter it was to be able to operate. So now, that being said, what's the current trends? So what are we interested on right now? What is the objective? So the real challenge that is facing the BCI community today is what we call getting BCIs outside of the lab. And that means to see whether all the results that were obtained within laboratory-controlled experiments do translate to the global environment. Whether in the uncontrolled condition of noise, BCIs are still able to detect the same brain activities, and also whether the BCI are ready to be able to be operated by healthy users and for non-clinical applications. What type of applications can we envision now that go out to the market for people to be really useful and not just as a gadget or a too cumbersome use? So there are two main approaches to try and get BCIs out of the lab, either to continue with the BCIs for explicit control, either through the reactive or active paradigms, being able to create devices that are operable by brain activity, or using BCIs for neuro-adaptation. In this case, the idea is to use a BCI as a means to get information about the user's states in order to adapt the interaction of other systems and interfaces. And interestingly enough, both of these approaches are highly synergetic with immersive systems. And that is my whole line of research. My goal is to use immersive systems in order to get BCIs closer to the market or the outside lab. And with an overarching goal from my research direction on designing interactive systems that are able to exploit in nearly real time the neurophysiological information of the users. Being able to exploit the fact that we have a tool to characterize the user mental state in order to provide the dedicated and characterized and individualized response. So here I like to quote one of my PhD supervisors that used to tell me, Hakim, your goal is to take two technologies that are not yet completely fully mature, on one side VR and AR in general, and the other side BCI, and hope to make them work together. How crazy is that? Well, I argue, at least I argued with him, and it was very successful discussions, that these two technologies, despite being not completely mature enough, are able to provide benefits to each other. And one of the results of my thesis was to present it in this type of framework, how AR and VR can provide useful to BCI and the other way around. So for instance, AR and VR offer new feedback modalities. The importance of the feedback in order to be able to modulate the brain activity is stressed out by the fact that having integrated feedback in the real world with AR, or maybe a completely controlled environment with VR, we're able to provide dedicated feedback to the brain activity. We also are able, thanks to AR and VR, to create controlled environments to study specific part of the brain. We are able to create protocols that are hardly reproducible otherwise in the real environment. And it's also a way for AR to bring interfaces, user interfaces to BCIs in order to operate with the real-world objects. I'll talk about it a little bit later. On the other way around, although BCIs are not yet completely working as expected or on par with other types of input devices, they are still a way to provide hands-free interaction for explicit control, and they are, as I was mentioning for the Neuro-Adaptation, a valuable source of information about the users that we can exploit. So regarding how this was used, for instance, there were a whole effort from the BCI community at some point to highlight how the effect of embodiment in VR actually could enhance the motor imagery effectiveness. There is a work that was conducted by colleagues from Portugal, Athanasis Varbopoulos and colleagues, who showed that actually being able to create a training protocol in VR, where the user was imagining rowing on a kayak, was able to increase the level of embodiment and how much the sensory loop was augmented. Similarly, in the same year, Ali Mardani and colleagues have shown that actually even providing realistic types of hand and avatar also had an impact of how much the users embodied their avatars, and in turn how that could provide useful for generating brain signals for motor imagery. So neurofeedback is the property of the brain that when displayed a feedback about what is happening when trying to, for instance, move the right hand, when delivering the real-time feedback, the user is able to modulate and with operant conditioning to learn how to better do the task. It has been used for a very long time with rehabilitation after a stroke, for instance, when people are not able to move their hands and to relearn how to reconnect the pathways of the brain to control the arms. But for healthy users, there is also a very, very recent trend of using neurofeedback, in particular in conjunction with augmented and virtual reality, to actually train athletes for performance. So an example of that was by colleague Wu and Al in 2025, where they actually show that just by providing a feedback about what's detected in the brain when doing a golf par, golf strike, sorry, I'm not very familiar with the sport itself, but that was enough to observe an increase of performance and on repeatability of the movement in the future sessions. Providing that neurofeedback was not only useful for rehabilitation, but could also provide performance for athletes. Going even further, Camille Genet from University of Bordeaux even created a startup, actually, where they are showing that by using neurofeedback, when athletes perform mental imagery, so for instance, a lot of athletes are adepts of what we call mental imagery, where they imagine doing the same movement again and again and again. When they are not physically training, they are mentally visualizing with a kinesthetic motion imagery how they are performing the throw, for instance. You can imagine a tennisman who is really thinking about how to do the throw, or basketball who is trying to do it. And by providing a real-time feedback from the analysis of the EEG, of what's happening, they notice that it is able to better train the users to perform the mental imagery and to target specific regions of the brain, and that is associated with a better movement after all. So the startup is called Neuroathletic, and I can tell you a little bit more about it later. So this is just examples of how BCIs can be used for neurofeedback. Now we'll talk about some of the results that we've been conducted. So just because I will talk a lot about SSVEP, steady-state visual evoked potentials, I prefer to make a quick reminder of what it is to really grasp what's the concept and what we can do with it. So imagine that this stimulus is flickering at 15 hertz. When you focus on a stimulus flickering at a specific frequency, your brain reacts with an increase of its activity at the same frequency of the stimulation. So here you'd have peaks at 15 hertz, 30, and 45 with the harmonics. Exploiting that for interaction consists on displaying several different frequencies and depending on which one the user attends or focuses on, we are able to operate. So for instance, with this little spacecraft here, by focusing on one of the wings, you are able to go left or right, and focusing on the cannon, you are able to strike. Sorry, I know it's been here for quite some time, and you can already feel how annoying it is. And you will see that's on purpose. I hope no one has epilepsy here in the room, and I think it's better and the same in the people attending remotely. So, first of all, we wanted to see whether this type of paradigm, the SSVEP itself, was operatable in AR, whether we could use the phenomenon or the brain pattern in order to interact with real-world objects using augmented reality. So first, what we did was to try and characterize the effect of head movements on the classification accuracy. Because one of the most interesting things of AR is that you are able to operate while moving, by being mobile, especially with HMD devices and the HoloLens at the time. So if head movement would have a significant effect on that, that would prove more difficult to use. So as expected, we found that there was a significant effect of the head movement, especially the amplitude and the speed, on the classification accuracy, but there was still a trade-off to be found, and towards limited motion amplitude was still able to operate. So we illustrated that through a...
Hold on, Hakim.
Yep.
Can you go back?
Yes.
What is on the horizontal axis? What are those degrees?
Yes, so the degrees was the amplitude. So if you can see from the video itself, there is the movement was a lemniscat of Bernoulli, trying to have something as smooth as possible. It was the time to complete the motion was fixed. So what changed was the amplitude of the movement. So 40
of motion.
Exactly, the amplitude of the motion. So for instance, 40 degrees was going from 20 degrees left, 20 degrees right, and 160 was almost all the way from the same directions. And as it was remained for the same time, so the speed was adapted. So we defined what we call the movement intensity. And on the y-axis, you have the classification accuracy of the SSVEP. So we did not look at into the spectral frequency themselves, but we used the classification accuracy as the metrics.
Have you tried when actually the triple flashing is fixed in the space regardless of the movement of the head?
Yes. And thanks, because I will come back to it. We have tried it, and we have some results regarding that. So to illustrate that concept, we have designed a robot control system on a 2D plane, where the user could operate the robot by focusing on one of the 3 fixed targets. And as you can see here, it's on purpose. The 3 targets are fixed on the center of the user's field of view, but there is also a condition where they will be fixed at some time. We'll talk about it later. And you can see here the user is able to operate quite nicely the robot between the 4 white dots on the ground that are supposed to represent the pathway. And this is in real-time speed. So the speed of the robot was kept voluntarily low in order to match with the previous results on the amplitude of movement. Yep, Andy?
Tracking where the user is actually looking, where they're fixating in this task?
Not in this specific video, although it was one of the plan, because you can see that there is a fiducial marker on the robot itself, but it was useful for the next steps. In the next steps, we have used contextualization in order to track where the user was saying was looking, thanks to the markers.
So SSVEP works best if you're actually foveating on the target, right?
Exactly.
And now you have a dual
Yes.
task where like I could be looking at the robot or I could be looking at the target.
Yeah. But if you can see here, the targets would remain on the center of the field of view regardless of where you're looking at. And we actually tested whether it has a significant effect to display the targets fixated to the central field of view, or whether to display them on the robot itself.
But even in that case, you have to sort of like saccade over to the target and attend to it, right?
Yes.
For it to work reliably, right?
Exactly.
Okay.
Yes.
So when you say focus on a target, that's what you mean.
Yes, exactly. It's overtly focusing. And I will talk about the notion of overt and covert and how you can do it. And there is actually a paper that we published last year on that, being able to do a covert operation of a BCI. So actually, following that results, that introduced me to how we can go towards getting BCI outside of the lab, because out of this result, the Orange company, which is a big tech and mobile phone company, kind of the equivalent of AT&T or T-Mobile in France, a really big company, they were really interested into our results on SSVEP and AR, and they wanted us to integrate that system into their commercially available home automation system, and said, well, we want to be able to operate the smart home using AR and SSVEP, and but without, of course, compromising the whole system. So this is the demonstration itself. It was a collaboration with Fouad Bouchnak and Inria Tech. So you can see here that there was three illustrative objects to display the concept. Here we had focus on where the user, we had information about where the user was gazing in order to only display the targets that were meaningful to the object within the field of view. So we really worked on how we can improve the user interface with two types of objects, one single command object, on-off objects, and also more complex objects that would trigger the apparition of a hierarchical menu, etc. So here was just the example of operating the fan, turning on or off the device, having a feedback of the targets themselves when depending on the state of the object. So you can turn on just to show you the TV itself with the hierarchical menu. And of course, here the targets were flickering at different frequencies to operate, but more is that they were able, when you select an object, to display different numbers of flickering targets depending on the concept. See, when you select the TV, then you're able to change the channel or change whatever you want. So this is an illustrative. But why I think it's important is that it's one of the first works. Yep.
What was the brain activity acquiring device in this case?
It's EEG. It's still an EEG with the HoloLens. It was the smarting membrane. Yes, exactly. Most of the results I will talk about in my work I will remain with EEG and HoloLens as a device. So why I think this is important to illustrate how BCIs can get outside of the lab, it's because for the first time, we were not just developing something out of research and prototypes, but we had strong constraints for the company themselves because they wanted something that they could be operated and that could be displayed in conferences and venues. So we had the system specification that the system had to be, that were able to operate different types of objects, single selection and hierarchical menus, that the system had to be asynchronous, meaning that we had to design a specific classification algorithm that we call the HTCA using hidden Markov models. I can talk about it later on if necessary. Meaning that we had to make the difference between the user willing to interact and simply looking at the target to understand the nature of the menu. And this is one of the biggest challenges in BCI. The modularity, so the system itself had to uncouple as much as possible the BCI from the rest of the system, meaning that they had the home in, which is the smart home system from Orange, that they could operate from the Mosquito protocol. But what they wanted is that voice and gesture, which were already implemented, would still work. So we had a software architecture where the BCI was uncoupled and would simply send commands through a middleware that would handle, depending on the context, the command itself. I will talk about the middleware later on. And they also wanted to have something that is hardware independent, meaning that we could just as much change the AR headset and the EEG device, and still that would work the same way. In terms of how the middleware work, it's actually it's similar to a finite state automaton, where it all starts with here the wait state. I will try to use the pointer. So in the wait state with the beginning of the system, the entry point, and whenever a new frequency is detected, meaning that the SSVEP responds that okay, the user is focusing on this target, then depending there was either no match, meaning that there was a false positive, there was a frequency that was detected from somewhere else, maybe there was a TV flickering at a different frequency, nothing would happen to avoid false positives. And if there was a match between the frequency detected by the SSVEP and the frequency map, so we had like a map of all the frequencies and the commands that they operate, then we would select depending on whether it was a selection object or a direct command. If it was like turning on the light, then the command would be sent directly and then transferred to the object through the Mosquito protocol. And if it was a selection, then we'd go back here, update the frequency map in order to display new selection and new hierarchical menus, introducing new objects, and so on. And what we did here that was kind of interesting was that we enabled to easily add new objects just by updating the frequency map and saying, okay, I have a new frequency to detect and a new command to associate to it, then the BCI would work continuously. We don't want to re-implement depending on the targets you wanted. We uncoupled that part from the system. But still, it was quite annoying. having these flickering targets all the time in your field of view was kind of simple, the way how you display them. So we actually studied the different ways, or we tried to characterize the design space of how you could put the targets. And that answers directly the question that you had. So we investigated whether the targets would better be frontal or horizontal, depending on where the robot is, to be parallel with the robot, whether they would be fixated to the user's field of view or fixated to the robot itself, meaning that if the robot would move there, the targets would remain in the same place, or whether they would follow the user, and whether you explicitly associated the target with the direction of the robot and the size of the targets, whether it would be adapted or not. So that gave us 32 different display strategy. Sorry, again, it's going to be flashy. We evaluated that into an experiment with 42 people that labeled the level of annoyance from the targets, as well as how much they understood easily the intuitiveness of the interface itself. We also studied the trade-off of the different ways to display with the classification frequency, classification accuracy, and we ended up having central targets within the field of view was what had the best classification accuracy in fact. So, and here I am switching more towards, oh, that's weird. Let me just stop here. Okay, anyway, that's not the right screen that is displayed here. It's stuck. So now I'm coming to what we actually did within the scope of my internship here in 2019. So we wanted to see whether we could actually act on the display strategy of the targets themselves to increase the level of user friendliness. So we were interested into reducing the contrast of the targets. There were results at the time that suggested that by reducing the contrast, meaning that the flashing would not go from full black to full white, but levels of gray, that would make it less aggressive to the eyes and provoke less eye strain. But the results also show that the less contrast you have, the less classification accuracy you had, or the more difficult it was. So we thought that maybe we could compensate by augmenting the size of the targets. So this study was about evaluating the cross effect of both size, medium, small, medium, and high, and big, with a different level of maximum luminance in order to improve the classification accuracy and reduce the annoyance. We confirmed actually the significant effect of the sizes. We found out that the bigger the size of the targets, the more easy it was to classify them, but also the more annoying it was. But there was no significant effect of the contrast. So here we could use a different level of contrast and have roughly the same classification accuracy levels. And this was kind of puzzling, but I will come back to that later, because when we compared that to a paper published in 2022 as well by Ladouce and colleagues, the results were different. But I have an hypothesis for why. Regarding the subjective preference, the same. The larger the targets, the more annoying to the eyes they were deemed, but we did not have any effect on the contrast either. So the user did not find that reducing the contrast was actually better for the user friendliness. And that contradicted somehow the results of the literature. But what we did very differently is that first, before using just the luminance itself, we had investigated the true level of luminance depending on the software level of luminance. And that's something that I did not find in other paper literature. So meaning that when stating that we had 50% of brightness from the software, actually that was way less than the real luminance generated by the device itself. It was a VR HMD. So that was promising, but yep.
So this on the horizontal we have the percentage of the luminance in the video memory.
Yes.
From 0 to 250.
Exactly. We're using a photodiode.
And on the vertical, we have the actual measured luminance.
Exactly.
Okay.
Exactly.
So this is pretty much the non-linearity of the display
Absolutely.
of the augmented reality glasses.
Exactly. So, but here I think this is kind of more robust as a way to really investigate the level of the contrast luminance you have. And that also may explain why, by actually displaying at 50%, when you, by software, you do it 50%, you actually have less than 50% of classification, so that of maximum luminance. So that's why could potentially explain the difference in the results that we had with the literature. So this was promising, but not enough. So we thought about why wouldn't we do it differently and change completely the nature of the stimulus. And this is one of the results that I'm most proud of that we had obtained here, something that we patented. And we said, can we just replace completely the flickering stimulation by something much more pleasing, by what we called bio-inspired stimulations. And on the pilot data, we have shown that actually focusing on the edge of the wings that flickers at a specific frequency triggers the same type of brain reaction than SSVEP. That was really promising. Since then, the result was in 2019. Since then, there starts to be papers that are talking about steady-state motion visual evoked potentials, but still nothing with the idea of having bio-inspired stimulus. So wink, guys, if you want to continue on working on this.
Hey, we have the patent.
Sure, you do. So, okay, but to answer now the question of Andy about how to overtly gaze on the targets, within the scope of the PhD of Arne van den Kerkhoff, that was one of my first PhD students with KU Leuven, we were interested in whether we could actually really operate a reactive BCI, here it was the case of the P300, an event-related potential, without overtly looking at it. So usually when you do a BCI, you have to overtly, meaning that you have to put the center of your field of view on the target you want to select. And then comes the usual question I have in my talks, yes, but what's then the difference with an eye tracker if you have to look at it? And then my usual answer is that yes, results have shown that it was modulated by attention, meaning that you can make a difference between just gazing at a target and really intending to select the target. But that was just the answer in theory. So what we wanted to do was whether it was really the case and whether we could really do that. So we introduced experimental protocol where we had three types of conditions. The overt visual spatial attention, meaning that the user would gaze at the target the user would want to select. This is a classical approach. The covert visual spatial attention, meaning that here the user would attend the center of the field, like meaning looking at nothing, but using the right or left side, like the extreme of the peripheral vision, in order to select a target. That's called overt attention. I focus on this on the center, but my attention is here on the side. It was classical. But what we introduced as well was what we called the split visual spatial attention, whether a user could actually gaze at a target that is flickering, but attend another one. Meaning that I'm in the center of my field of view, I have a target, but actually I'm focusing on another one. And we introduced a specific algorithm that was based on realigning the different trials in the training, and we found out that it was indeed possible to operate that. Of course, the classification accuracy was not on par with the classical overt, but still this is possible to determine what is really the intent of the user and not only where the user is gazing. So this is a...
Whether or not I'm looking at the yellow target or the other target? Like, is that a binary classification?
Yes, it was basically you had several targets, and here meaning that the classifier detects that what you are selecting is this one. It was the one that the user was supposed to attend, but the user was instructed to gaze at one of the green targets.
But your classifier is like trying to figure out if you're looking at which of those
yes.
targets.
Not only whether it was the yellow or not, it was which of them you're looking at.
So you're getting some power by casting it that way.
Exactly. So it was a 6-class classifier, and not only a 1 class, just focusing on that target.
So technically, the research question here is, when we get our response in the visual cortex to where we're looking at or to where we pay attention to?
Exactly.
Okay.
That's exactly the research question, and the answer was that yes, you are from the visual cortex. You're able, not only the visual cortex, because this was also P300, so there was also the cognitive part of that you are attending that target. So you still have the VEP from your visual cortex because the target you're gazing at is flickering. But as you are attending another one, the P300 is delayed. So by trying to realign the ERPs, you are able to detect which one you're actually attending, and not only the one you're visualizing. So these were examples of how we could use BCI in order to operate virtual reality or augmented reality systems. But there is also another way, or the second approach, on how you can get BCI outside the lab, and that is focusing on what we call passive BCI. So the concept of passive BCI was formally introduced in 2011 by Thorsten Zander and Kristen Cothi. And that's the type of BCI that enables you to characterize the user mental state. So for instance, mental workload, the level of engagement, focus, and this type of things that you are able to detect from the EEG. And the intention here is not to send a command. So BCIs are not, passive BCIs are not BCIs that are supposed to send commands. Although, I have a very nice example here that I like very much, which was introduced by Zander and colleague in 2016, which is called the implicit control. So this is an example where the user was just, without being instructed, just gazing at a target that we told them that was supposed to reach the selected or the highlighted area. And at the beginning, the target would just randomly go in directions. And whenever the target would go in an opposite direction to the target, there would be an error-related potential detected in the EEG. So error-related potential is a brain pattern that happens when the user notices something is wrong, like an error. The oh shit signal, sorry for the term, that's how it's called. And with that, they could adapt or adjust the probability of going to different directions, and the targets would ultimately end up going to the selected target by the user implicitly controlling it. And I kind of like it because it's also without consent operating of a BCI. Just because you're witnessing something is wrong, we're able to adjust the parameters. So that's really interesting. But in general, the procedure or the methodology that we introduced within the frame of a European project that I led within the last 4 years with ETH Zurich, INRIA, and Essex and University of Koch, we introduced this framework about how we can create neuro-adaptive systems. And it all comes from detecting specific neuromarkers. So in order to create a neuro-adaptive systems in VR, what you need to do is to understand what part of the brain you are measuring in order to be able to operate your system. And then once you have identified that neuromarker, you start designing specific real-time classification systems. And then you use that to adapt to the system based on to the user based on their level of engagement or whatever else. So to illustrate that, I will talk about an experiment we did in collaboration with TU Graz, where we wanted to see whether we could detect system errors in VR, whether errors that were originating from the system and not from the user still elicit error potentials. So we designed a task, which is a pretty simple pick-and-place center-out task where the user had to grab the object and just drop it in the corresponding shape. So pretty easy, kindergarten kind of task that my son would love to do right now. So the cylinder goes in the circle and whatever. So what we did was to introduce different types of errors. For instance, simulating the tracking error. Here, while the user was displacing the object towards the target, we would simulate a tracking error loss, meaning that the object will remain frozen mid-air, and the user would not be able to complete the task. That was simulating that the tracking camera lost track to object. We also introduced what we call the feedback error. Here, the user would drop the shape in the correct place, but would get a negative feedback, red. And the background anomaly was something also we were interested on, having something weird happening in VR that was completely unrelated to the task, something that was just on an error of rendering of the task, whether that elicited error potentials. So you can just check the papers if you want the detailed results. What I highlight here is that we were not really able to classify in single trial the feedback and the background anomaly, supposedly because they did not really impact the user doing the task, but we still detected with more than 80% of single trial classification the tracking error, showing that yes, it was possible to detect tracking errors and these types of impeding anomalies in VR and detect it. And that opens the way, for instance, to automatically tagging errors happening in VR. This was submitted to IEEE VR. Yep.
Yeah, question about that. Do you think it might be possible to distinct or to actually detect whether the user thinks it's their fault or the system's fault?
That's a good question. Actually, we designed the experiment in order so that they did not have this effect by telling them that it was a system that we were designing that might have errors, we apologize for that in the beginning, but we told them that it was not their fault. That the system was still a little clunky so far, and so that was also part because we wanted to have something that is specific and stable into how they behaved with the error. If we did not tell them that, the object being frozen, some would go back to it, and that would introduce error potential, like motion artifacts, muscle artifacts. So we told them the system is not perfect. We had like 25% of errors sometimes, and we told them if that happens, just continue your motion as if nothing happened. Just finish the movement in order not to introduce artifact and really to isolate the error potential. So yes, that would be interesting to see whether the fact that they believed that it was their fault would provoke a different type of error potential, but not in this case.
But here they know that it is not.
Exactly. Here it is not. And that's also why our hypothesis on why we did not get as strong error potentials in the two others, because the task is too simple. So even if you drop the cylinder in the circle, if you have a red feedback, well, you know you did the task right. So there is no cognitive, negative cognitive feeling associated to that. The same goes with the background anomaly. It was rare enough, but did not really impact the task. So you might even notice it or not. So that's our hypothesis, and we would like to go further on that. And we wanted to pursue this approach on using passive BCI in order to improve the user experience in VR by working on how we can characterize the different dimensions of user experience. So within the frame of the Genesis project, we worked on different types of dimensions of user experience, the sense of embodiment, the sense of presence, and the sense of immersion, all these type of things that characterize how well the user is doing in VR, not only in terms of performance, but how the general experience is, whether they feel embodied in their avatars, whether they feel present in VR, and these kind of things. And we also highlight the necessity to first identify exploitable neuromarkers. I really am against the black box approach saying that, okay, here the users are feeling present, here they are not, what's the difference between the two? I really start by investigating what from the brain can be exploited for that, and I will tell you why later on. So within the frame of the PhD of Gaël van der Leer, who defended last December, we investigated specifically how BCI and passive BCI can be used to tackle the problem of cybersickness. I don't know if you're very familiar with it, but I have a quick reminder. So cybersickness is the feeling that a lot of people have when they use VR that is very similar to motion sickness, nausea, dizziness, and all type of not feeling very well in VR that really impedes the users to perform the task. So the formal definition was say that it's the nausea, headache, and dizziness experienced during and after VR immersion and can last for quite some time after the experiment. It affects potentially up to 95% of the users if you go to more than 20 minutes. And it can lead to premature experiment termination, and even the effect lasts longer after. So this is a crucial problem for virtual reality. And we believe that here, BCI can provide a solution. Something not only to detect cybersickness, but maybe to anticipate it. So that's an example of how BCI can get outside of the lab by providing useful for a problem from another discipline. So cybersickness is measured using different ways. Either the subjective measures, we have the SSQ and the VRSQ, which are the most famous questionnaire to evaluate the level of dizziness and nausea and so on. And they have their limitations and cons and pros. The fact is that they are retrospective, meaning that we perform the SSQ after the experiment has happened and ask them, how do you feel? So we're not able to get it in real time. And it's sampled at discrete time points. So you can have different blocks, and between the blocks, you ask the user to fill in the SSQ, but you cannot really know what time specifically started to trigger the cybersickness. It has other biases, like the recall bias, because when they compare between conditions, and it's basically subjective. And there is, from the other side, objective measures, EEG being one of the most popular right now. So there's a whole bunch of papers and literature on using EEG to detect cybersickness, which has the advantage of being continuous, basically. And although it's affected by cross-subject variability because the markers are not the same. So what we did is that we conducted a survey that has been submitted, so it's under review at TVCG, where we identified couple of hundreds of papers using a very specific, this is not the exact request that we put on Web of Science, PubMed, etc. So you can have the exact one on the paper. So we used EEG, BCI, motion sickness, different names. So this is just to illustrate, but we had all other combinations. We follow the PRISMA guideline, so it's a reproducible literature review. And we ended up selecting 83 papers included that we analyzed. All these papers used EEG to detect cybersickness. And that illustrates something interesting. First is that most papers studied, focused on the classification, basically.
Can I move back? That's something interesting.
Yes.
I like the methodology of reading and classifying the papers. How we do this, by hand or using some large language models?
We did it by hand.
By hand. So
Yes.
if somebody reads the papers and basically rejects or merges.
Yes, that was the first year of the PhD of Gael. He really attracted all the different results. So we read the papers together. What we did is that we read first the abstract in order to select the elements, whether they were mention of EEG, etc. So there was first a screening, and then the records, and then the papers that were selected were read more carefully and thoroughly.
Because technically literature research is a foundation of any research work.
Exactly. And to be honest, Gael tried with LLM as well, just out of curiosity. It was the recording of the first recording of the papers was in 2022, I think, and then we did an extension, like an update in 2025 when we submitted the paper. In between, LLMs had progressed a lot, so we wanted to check whether we could have similar results, but we did not yet trust fully to just drop in only LLM's results. So it was done by hand. But I guess this is typically the type of thing that you can automate and have results out of it. So, and also something that is interesting, it's not yet the case, but we intend to release the data set that was recorded from that. So all the references, the targets, how we classified them, that the CSV file, we will release it when the paper is finally published.
This is something an LLM can do.
Yeah, exactly. That's typically the case.
Guidance from the researcher.
Yeah.
And save a lot of time for the literature research.
Absolutely, I completely agree, and that's something that we would like to compare between the two. So out of the literature review, what we found out is that classification is the most reported objective. So most of the papers that combined EEG for cybersickness, what they were interested on was to say whether we could classify whether the people were sick or not. And most of the correlates, when they were interested into finding a neuromarker, they only focused on alpha, beta, gamma, and all the classical spectral components. And that's actually kind of problematic. And you can see that it's a booming research field. Really, the number of papers is exploding. I think more than half of the papers were published between 2020 and 2025 when we updated the search. And that's actually quite a problem because some of the results may be, let's just say, optimistic, to say the least. Because if you follow the literature itself, 100% of classification accuracy of within subject was achieved in 2010. And even cross-subject, meaning training the classifiers on subjects and then testing them on new subjects to detect cybersickness, was solved in 2020. And we still know that it's actually a problem. That's still a problem. We know that problem is not solved. So that's the risk when you're actually focusing on the classification itself and not going to the root causes of what causes cybersickness to anticipate that and really to be able to prevent it from happening. So for that, we really wanted to go back to the etiology of cybersickness. What causes cybersickness? So there was this was one of the topics of the survey itself, trying to navigate through all the different theories and all what we know about cybersickness because it's something that is not completely yet understood. So there were several theories, not all of them completely, mutually exclusive. So some of them are based on the others. Well, spoiler alert, I will talk about the sensory conflict theory more because it's the most prominent one, but I wanted to show that there were others as well. The postural instability theory, for instance, posits that because when in VR, we don't have a stable frame of reference, so the fact that the body spends too much time trying to adapt the posture is what actually causes cybersickness. It's the too long instability. We have also some theory that posits that it's the vergence accommodation conflict because the eyes on what they are focusing on when the objects are close. It's what actually provokes dizziness because we also have cybersickness in, for instance, in 3D screens. So it might be not only related to the sensory conflict theory, but also to the vergence accommodation. Interesting one is the poison theory, which is an evolutionary explanation saying that the brain actually interprets the fact that we have different senses that are sending different informations as being poison. And the nausea that arises from that is because the brain tries to eliminate the toxin. You have the predictive coding framework, which is one of the latest theories that is very interesting as well, and states that it's because the brain continuously tries to predict the next outcome, and when having different responses between the vestibular and the visual system, that causes maybe a problem. It's because they are trying to adapt. Or you have the good old sensory conflict theory that posits that it is when the brain receives contradictory feedbacks from the vestibular system and the visual system that causes cybersickness. And that's interesting because that's really linked to motion sickness as well, the theory itself, but oppositely. When you are in a car, there is an experiment you can do that if you're reading your phone or a book, that's most likely to make you sick in a car. And that's because your eyes are fixated on a fixed point, but your inner ear is telling you that there is motion. And that's the supposition of why, or the hypothesis of why you're getting sick. In VR, it would be the opposite. It's because your eyes are telling you you're moving in all the directions, but in fact, you're just remaining still in your living room. So your inner ear tells you you're static, while your eyes are telling you you're moving. So that's the sensory conflict theory. And by the way, this is generated by AI. This is the only image and the first image that I generated by AI to illustrate the sensory conflict theory. And I really liked it. So I kept it, but I wanted to have a disclaimer. Yep, Dimitra?
What else that comes to mind, and I don't know if any of these theories talk about it, maybe the sensory conflict. When someone is in VR, because the field of view is limited, we're constantly moving our heads. So I wonder if any of the theories talked about if we were in non-VR environment, normal environments, and you have someone move their head at the same rate as they do in VR, do they also get the same sickness coming up, right? So because we have like the 180 kind of view, okay, everything's blurred out, but things are static. Versus in VR, you're constantly trying to see what else is there.
Yes.
So I wonder if any of those theories account for that.
That's actually a very interesting theory, and I think it's completely worth investigating. I'm not aware of any study that specifically targeted that, the frequency of the head motion into that, but I will show you in the rest of the slides the experiment that we conducted, where the user was instructed not to move their head, but still we had some correlations with cybersickness.
On field of view, and we did a paper on that. It's probably already been 10 years ago on making even a low resolution.
Exactly, blurring sometimes, yes.
Rendering in the headset. Yeah. It was not something we really focused on, but it felt like there was something there.
Absolutely, but yeah, there are papers that instead of trying to go to the causes, try to work on the field of view, sometimes even reducing it in order to mitigate cybersickness. So that's the idea. When you detect that someone is getting sick, what can you do? Maybe you can lower the resolution, maybe you can just turn off the screen for a moment, maybe you can stimulate the inner ear. So it's about what we can do. And I think I know the paper that you're mentioning on how you can just change the resolution, augment the field of view. And there are all kind of mechanisms that you can implement to correct it. Yeah, for instance, yes.
That's probably going to help as well.
Exactly. So based on this theory of the sensory conflict theory, we said, okay, can we really investigate the cause itself? Because feeling the motion from the eyes and not the inner ear has a name, and it's called vection. So vection is the visual illusion of self-motion in a stationary observer. And it's best illustrated with a train example. It all happened to you, I'm sure. You're sitting on your train, and the train next to your one starts. And then for a couple of seconds, you believe that, oh, we are moving. That's exactly your eyes tricking your brain to believe that, okay, you are moving. That's a visual-induced motion of motion, visual-induced motion, illusion of motion. So our hypothesis was that by detecting vection, we could maybe detect a pattern that precedes cybersickness. And then we can intervene, maybe reducing the field of view, closing the eyes, before the users get sick. So the properties of vection is that it has been shown to increase the level of presence. The more vection you feel, the more present you feel in VR. That makes sense, because if you're on a roller coaster, but the roller coaster does not trick your brain to believe that you're moving, you're less present. It has also been so far detected to co-occur with cybersickness, but no really relationship yet between the two, maybe causality effect or stuff, but we know that it's central to the sensory conflict theory. So we again conducted a survey on using EEG to detect vection in VR. This has been published in the Graz BCI conference, I think. Well, honestly, I forgot where we published it, but that's the link where you can have it. So we investigated with the same PRISMA guidelines with different. We only identified 16 actually studies that really used EEG to detect vection. Out of those, there were several spectral components that were identified all around the place, alpha, beta, gamma, whatever, but the most stable ones were the alpha band modulation between 8 and 13 hertz in the parietoccipital region. And that was found to be transient at the vection onset, at the moment when the vection started, but to remain increased after the vection is established. There was also a direct correlation with the subjective vection intensity, being that the more vection you feel, because it's actually not a binary state of vection or no vection, it's the level of vection you feel, that was correlated with the level of the spectral components. But in terms of ERPs, there were a few results, but none was related to the vection intensity itself, meaning that we did not find in the literature anyone who found a stable ERP related to the intensity of the vection. So we investigated that. Our hypothesis was that vection onset was a time-locked phenomenon, meaning that there was a time where the user would start feeling vection, just like in the train. The moment the train starts, that's when you start feeling that, okay, I am moving. There is a time zero event. So we designed an experimental protocol, and this paper was accepted at TVCG a couple of weeks ago, actually, where we investigated different levels of acceleration. So here the user would remain static for some time, then a small acceleration, and then a strong acceleration. And we considered our T0 as the strong acceleration or the strong deceleration. Really the moment where we change the flow, the optical flow of motion, whether that would create a specific pattern or vection. So in terms of apparatus, the users, there were 30 healthy subjects. They were equipped with 14 central electrodes. Our hypothesis was that there were no reason for the phenomenon to be lateralized. So if it happened, it had to happen in the central region. So the 14 electrodes were displayed in the central field of the central side of the brain. And we used the valve index HMD because of the higher frequency rate. And also, you will see it in the video, in the next video, we used a minimalistic VR environment to simulate motion. So the user would remain static, and then the environment would move so that to make them feel vection. And we investigated how much sickness they felt by displaying the SSQ questionnaire after each block, and also the Likert scale vection. So after each trial, they were asked to report how much vection they detected. But the vection itself is difficult to characterize. What is vection? How do you know that you have felt vection? So what we defined is that we told them you can either have the feeling that you were the one moving while the environment was remaining still, or you were still and only the environment was moving. And depending on the levels of how much you were moving or the environment was moving, we defined 4 levels of vection: no vection, small vection, medium vection, and high vection. So the experiment itself looked like this. The user was equipped with a VR headset and the valve HMD. The environment was minimalistic, just white spheres, not to introduce any confounding factors. That's the most used protocol in the literature. And then here, for instance, there is a strong deceleration towards the back. And we hypothesized that, okay, that is the onset of when vection would start. And then after each trial, the user would state how they felt vection, then again, remaining static, then a small increase of speed, and then after a random time between 3 and 5 seconds, there would be a strong acceleration forward, and then coming back to the classic, while EEG was monitored. Out of that experimental protocol, we found out several markers, actually. First, we found a marker of acceleration in virtual reality. We saw that the acceleration itself in the CZ electrode triggered a specific brain reaction, regardless of the direction, but between a static or small acceleration and the strong acceleration, we could detect that out of analyzing the EEG. And more interestingly, we could even detect the direction of the movement out of the FCZ electrode. There was a marker of the direction of movement. And in terms of vection, we also identified for the first time a significant marker that was different between users stating no vection or a weak vection with a strong vection, with a difference. And we were really surprised because this marker appears to be a P600, like appears 600 milliseconds after. There were several hypotheses to explain that. Yep.
How did you ask this question here? Was it because the user sits in a chair? I don't know why anybody would say that they're physically moving. Maybe you mean that they're moving in the virtual world?
Yes, moving in the real world, of course. It means like, do you feel like you are in a spacecraft kind of thing? Because this was supposed to be like a galaxy, white dots advancing, and whether you feel that in VR you're moving.
It's a point of view.
Exactly.
Not a physiological.
Not a physiological. They knew that they were sitting on a chair. It's not about that they are physically moving. But I'm not sure, I'm completely allowed to talk about it. This is a follow-up experiment we're doing. So we're also introducing physical motion to compare. But we can talk about it off camera maybe. So yeah, interestingly, the P600 that we found was very similar to actually a marker that was found in the vestibular stimulation. So there was a similar experiment where they actually moved people really and then investigated whether a congruent movement or not would trigger an ERP, and it's very similar. So it's very promising because it could potentially mean that you can, in VR, trigger the same effect on the vestibular system as you would in a real motion. So in terms of remaining challenges in combining BCIs and VR, we still have the problem of the hardware transparency, meaning that having both an EEG device plus the VR headset on top of it is quite challenging and quite cumbersome for the user. I know there are a lot of efforts now onto integrating the EEG devices directly on the VR headsets. We have the synchronization issues, lab streaming layers and other protocols that enables to integrate different kinds of systems are present but are still not completely perfect. And you have to be very careful about the stimulation that you're providing and how you synchronize them. The identification of stable neuromarkers, if you want really to be useful for the VR community, you have to identify markers of presence, markers of embodiment, and so on. And of course, the real-time classification of the mental state, because all what we've done so far, this is aggregated across users, but we're still up to designing new algorithms able to detect those in single trial. This is another type of problems. And where are we standing at in terms of BCI? I really wanted just to highlight that. I guess most of you are familiar with the Gartner hype cycle that predicts how a technology evolves in terms of expectations. So it all starts with an innovation trigger that leads to higher expectations from the general public, and then a thorough of disillusionment because that, okay, the technology seems to be less than it expected. But after that, two possible paths. Either go to the valley of oblivion or go back to a plateau of productivity because we have focused on the core sets of what is possible. And in 2015, Gartner predicted that BCI, bidirectional brain-machine interfaces, would actually reach the plateau by 10 years, 5 to 10 years, that would be really into a BCI that is used and adopted and mainstream. Guess what? I found the 2025 one. And we're almost still there, the same place. Which is interesting because we did not go to the valley of oblivion, meaning that there is still a lot of hope into what BCI can deliver. But now they're more careful. They say more than 10 years. Meaning that at some point, brain-computer interfaces, I believe it, will become a more mainstream technology. Not forcefully for the application that we envision now. That's why I try to really diverse the way of BCI being useful, but they will reach the plateau of productivity, in my opinion. I think they removed it because they were afraid of it. They split it. So there is, I looked for it, but yeah, there is machine learning here. There is top. I did not see generative AI, for instance, into that thing. But there was, yes. But there was AI, I think, in this one. Decision intelligence, yes. Embodied AI, AI agents. That was the top pick. Inflated expectations. So AI maybe reached the top, of the expectation that completely disappeared from the Gartner cycle. And just to open up on some notes, what are the remaining challenges to get BCIs out of the lab in general? We still have the challenge. I have classified them into groups. The challenge that are related to the signal processing itself, the BCI inefficiency. We used to talk about BCI illiteracy. Meaning that some people, for some reason, like 30% roughly, would never be able to operate a BCI. Now it's a BCI inefficiency, meaning that it's a BCI that is not able to work for those. And we switched where the error was. The inter and intra-subject variability, that's also a big issue in order to be able to design algorithms that work across subjects. The data-related challenges, data availability and standardization. We also have hardware-related challenges, integrating multimodal data sources. I don't believe that we should be exclusive of the other, meaning that you have a BCI, EEG at some point, and then you cannot.
That's one of my questions.
Exactly. I'm not conservative on that point. Even in the experiment that we conducted on vection, we still had EDA. I think physiological computing as a whole is more promising, but I think the complementary nature of the different signals is what will bring BCI outside of the lab. We also have the user-friendliness of the measuring hardware, as I mentioned, but there is the in-ear EEG and so on. So you will understand why I ended up with these challenges. And the last one is the privacy-related challenges. There is much more now awareness about what the data could potentially mean if they are outside on the wild. So there are starting to be some protective measures that we are working on, actually, on those.
What do you think? Is EEG a personally identifiable information?
I have an ANR, which is kind of the equivalent of the NIH project on this, that we have submitted, and we're waiting for the results to be accepted and done. So I think EEG is not an identifying feature yet. So from the literature, there is no yet strong proof that from EEG you are able to re-identify a person. Although on smaller data sets, some results have shown that it's the case, but always some issues. But I think within the time frame of 10, 20 years, there are high chances that EEG will finally become that. So we're trying to investigate that question more thoroughly and see how we can protect the users from the identification leakage through federated learning and other types of means, but that's the scope of the project. So yet, despite these challenges, it is quite an exciting time to be doing BCI, and that is completely oriented to the audience here. It's still very promising. We are witnessing really a booming effect on designing, for instance, transformer-based models. I've never been a huge fan of deep learning for EEG. I know we chatted on that with Ivan and Hannes when I was an intern here. I always believed, and the results proved it from the literature, that simpler models achieved better, or in terms of trade-off, better classification accuracy than the fancy deep learning models that usually were less explainable and less generalizable. For these, the transformers, though, there was really a strong ground onto what they are bringing to the table, and I really think that's a promising direction to be following. And I can chat about that later. The hardware is also progressing. We're seeing new types of measurements, like the optically pumped MEEG, having portable MEGs that are not like the same huge rooms that we knew, the in-ear EEG. Saline solution-based EEG are now on par with gel-based EEG, meaning that when we compared between dry EEG and wet EEG, there was kind of a huge gap. But now there is like a trade-off between the two, and we have been using a saline-based solution, meaning 64-channel electrode that you just dump in, soak in a saline-based solution and put on the brain, and you have the level of impedance of a wet-based EEG, but much easier to operate. So it's really promising. We are also having progress reported in new tasks. For example, we have a PhD student now working on inner speech detection in EEG. This was, in my opinion, inconceivable a couple of years ago, but now we're starting to see results that we're able to detect between words because we understand better, we have stronger models. And we have a global standardization effort. The brain imaging data structure, the BEADS, that is the new standard for how you share data sets across different research organizations. You have the mother of all BCI benchmark, MOABB, that is trying to regroup all the data sets existing in order to be able to train those big models, transformer-based models. And as a conclusion, getting BCI outside of the lab is the overarching challenge. I think it's the most prominent challenge in terms of the BCI community, but it does not only require accuracy, it also requires to take robustness, usability, and ecological validity into the consideration, not only the classification accuracy. Immersive systems and BCI are highly synergetic, and I even believe that VR and AR will contribute to get BCI outside of the lab thanks to Neuro-Adaptive system that will enable to characterize, to adjust the VR experiment to each users. And just as a conclusion, I think the BCI field has never been this exciting, and the next steps is up to us. Thank you very much for your attention, and you have still questions, happy to answer.
Questions from the audience, questions from the remote attendees. Feel free to unmute your microphone and ask questions. Same thing is for the audience. It was actually quite interactive, but if there's still, Dimitra.
I think if you go back to the last curve, the excitement and
Yeah.
oblivion, right? I think something that has been keeping BCI lately out of that oblivion phase that has happened in the past is the advancement in all of the other fields, right? In
Absolutely.
deep learning, in AI, in LLM-based processing, in hardware. So all of these, I think, will keep BCI out of that oblivion phase because there are new things unlocked every 5 to so years, right? So.
Absolutely. The fact that the data sets are now being available, that are being shared, that are being structured in a standardized way will ultimately benefit the LLMs and AI models to be able to train across tasks. So I think, and that's maybe one of my personal opinions on the field, is that the future of BCI is not to remain on a paradigm specific, meaning that if we really want a BCI to be useful on the wild, it would have been to be a model trained across several tasks, and not training each task, each user every time. And that would be possible with the new models, in my opinion.
Yeah, because it is a technology that relies on so many other things.
Absolutely.
So it can always, right,
benefit from,
yeah,
absolutely. Yep. Andy?
So one of the things that I struggle with sometimes when I'm explaining SSVEP to other people is, people now know about eye tracking in VR. Right? There's pretty good eye tracking, and like I'm just curious, like, what's your?
Well, we're transmitting, but
I'm just curious what your where you sit on that. Like, how do you talk to people about SSVEP and, like, in this
How do they
kind of question
compare?
of why not just use an eye tracker?
Yeah. No, and I not only have been talking with to people with that. This is the question, and thanks for bringing it in, because that's the question I have in every single one of my talks. You can even check the one that I on YouTube. I always have this question when I talk about SSVEP. And maybe secretly that's one of the reasons why I switched out of SSVEP, not to get the question anymore. But no, more seriously. Yes, I think, and that's why we did that work with Arne on the covert and split attention. The answer is that yes, eye tracking is also progressing, but you're still having this issue of the Midas touch. Basically, looking at the target is looking at the target. I think, by theory, SSVEP is supposed to be modulated by attention, meaning that I can make a difference between just looking at something and really intending to send that command. It's yet difficult. It's theory. It's only theory so far. So that's why we really said, okay, how can we prove it? Can we look at a flickering target and selecting another one? That would be something really to prove that by a difference of an eye tracker, I'm not only saying that, okay, where am I gazing, but really sending something. Because if you just look at the eye tracker, usually it's simple commands. But if you have something complex that you have to look at to understand what it does, even the longer the dwell time you put, the more annoying the system finds out, and you have difficulty finding that perfect dwell time. With SSVEP, there would be no need for dwell time anymore, because if you're just gazing at that for long enough just to read it and not as selecting a command, it can make the difference. So that's how I stand on that regard.
Okay, thanks.
more questions? Dimitra?
No, going back to what you said, if EEG is identifiable information, right, on that topic, when it comes to legal or IRB type of processes, it is considered a biometric measurement, and so for those reasons, we do treat it as identifiable, and I think it's a good practice to be in that space early, treat it as identifiable information. Yes, as you said, maybe it hasn't been exactly proven yet, but it may be a matter of time and of technology, of signal processing, of whatever that may be. But perhaps even EEG plus heart rate could be a killer combination to identify, right?
Absolutely, you're completely right, yes.
for all of the studies that we do treat it as identifiable information, so we go through all of the processes for IRB, etc.
So that's really something that I'm interested in. There is even a book chapter that I wrote that was titled Towards Neuro-Ethical Law. It was a chapter book in French. It was for the OECD and especially for the European Union, like an effort that we're doing. I totally agree with you. That's why actually in the project that we're conducting right now, we are interested in designing procedures to make EEG anonymous. So we're working actually on a project where we could potentially remove the identifiable features if we found out, and only keep in the data set the features that are needed for that task. So that's a challenging task, because when you don't know what are the identifying features yet, it's difficult. Plus, you don't know exactly what types of utility features you're looking. But it's a collaboration I have with Mohamed Maouche, who is a colleague from INRIA Lyon, who works on the privacy field. And he does that with voice. He does that with different types of other signals. But the challenge for EEG with the low signal to noise ratio is really interesting for him. So that's an ongoing project that we're tackling. And in terms of IRB, I think in France there is a good or a procedure that I would recommend is what we call la clause de revoyure, or the fact of checking back regularly. So some IRBs said, okay, you can share it because, as you mentioned, we need those data. We need to share data because between researchers to be able to progress. If everyone treats them as sensitive data that we cannot share, and everyone just remains with their own data, we will never reach out that breaking point to get outside of the lab. We need to share that between ourselves. But the procedure is encouraging to recheck every 2 to 3 years whether there has been progress onto the identification from EEG, and then to make a decision. So far, no groundbreaking results, so we're still able to share it, as long as you don't include any other identifying features in the data set.
And you can take the example of speech, also identifiable, but very easily shareable now, right?
Exactly.
Across the communities. Or
With federated learning and with other means. But the difference is that speech is much more better characterized. We know exactly the types of frequencies. We have the language to know exactly what types of, and I'm speaking to the audio group, which is much more knowledgeable than me on that. But I would say it's not easy, but much easier than in EEG. In EEG, it's a much more difficult task because you don't know what is the utility feature. That's the idea. Other question?
No questions? Audience?
I have one more point for discussion, but
I will remain around here, so I'm happy to continue chatting.
So if there are no more questions, let's thank our speaker today.
Thank you very much.
Thank you, Hakim.
Thank you for attending. Thank you.
Thank you for coming to this talk, both physically and virtually. With this, we close the talk. Thank you very much.